From Army headquarters in Washington to the far-flung outposts of our military forces, radio circuits must be constantly maintained. Skilled engineers tend the transmitters that send their signals across the world and complete the circuit to San Francisco, Tokyo, or Berlin. Distant installations must have similar apparatus. In combat, the utilization of remote and isolated forces demands communication by radio with higher headquarters, sometimes over long distances. There is more to maintaining these radio circuits than simply throwing a switch and speaking into the microphone. As you know, if you've ever listened to a transocean broadcast.
This is Robert speaking to you from London. The news today is on a threatening note. At 10 Downing Street,
Due to technical difficulties beyond our control, this broadcast from London will not be continued.
To overcome as much as possible these technical difficulties and to bring them under control, military and civilian scientists conducted extensive research. Army channels cannot be cut off as safely as a commercial broadcast. There is too much at stake. Marconi proved by a transatlantic test many years ago that long-distance communication was possible. Ever since that time, scientists have been trying to explain fully what happened so that communication can be made more reliable. What did they find? Let's begin with some fundamentals of radio transmission. When an electrical current alternating at radio frequency is fed into an antenna wire, an alternating magnetic field is set up about the wire. This alternating magnetic field gives rise to an alternating electric field, which produces a magnetic field, and so on. This wave of electromagnetic energy is radiated from a normal antenna at all angles and in all directions. The action can be generally compared to expanding ripples on the surface of water. The energy used to disturb the water's surface is propagated through the water by waves, causing the light ball to bob up and down. When the electromagnetic energy radiated from the antenna encounters a receiver aerial, an alternating electrical current is produced in the wire by the radio wave. Thus, contact is made and signals can be received. This pretty picture of radio wave propagation is unfortunately complicated by various properties of the Earth mass and the atmosphere. It is further complicated because radio waves of different frequencies behave in different patterns. In general, radio waves are propagated as ground waves. That is, the wave tends to follow the surface of the Earth. Or as sky waves, which go off skyward. The ground wave, familiar to us as the one used by commercial broadcasting stations, diminishes in amplitude with distance. Its energy is also dissipated into the earth as heat. Pictured is the surface component of the ground wave. It is the method of propagation for low frequencies where the antenna is close to the ground in relation to wavelength. In very high or microwave frequencies, the waves are closer together. They move out from the antenna in straight lines and do not follow the curvature of the Earth to any great extent. We will consider only the portion of the waves which travels in the desired direction. When the antenna is high above the Earth in terms of wavelengths, the space wave component of the ground wave predominates over the surface wave. Radio waves from a transmitting aircraft reach a receiving aircraft by means of the space wave. The space wave has two components, the direct component and the ground reflected component. These two waves, upon reaching the aircraft, may add or cancel. Generally, we are concerned with that portion of the radiated wave that does not follow the Earth's surface but starts out skyward because of the particular properties of the antenna and of the Earth. Obviously, such waves would be of no use to us if they did not in some manner get back to Earth. Some of them do. When very high and microwave frequencies encounter layers of the atmosphere under proper conditions of temperature and humidity, they are refracted and bent back to the ground. These waves may continue outward, confined between the Earth and the atmosphere layer whose abrupt change in conductive properties has refracted the wave. Sharp changes in either water content or temperature of the atmosphere are caused by weather conditions and are difficult to predict. Radio waves of a less high frequency also come back to the Earth. They are returned by the ionosphere. These waves may also continue onward, guided by the channel between the Earth and the ionosphere. With these main types of radio wave behavior at our disposal, why have we selected the wave returned by the ionosphere as the key to long-range radio communication? Well, let's use the process of elimination. The wave that travels along the surface of the ground might be useful for long distances if its energy were not absorbed so quickly. Too much power is needed in the transmitter to push this wave very far, and the space component of the ground wave is limited to nearly line-of-sight distances. Cross them both off. The wave that is refracted by atmosphere weather conditions might be useful for medium distances if these weather conditions were constant and predictable. They are not. Cross it off. We are left then only with the wave that is bent by the ionosphere. We'll have to use it. Although subject to changes, irregularities, and disturbances, the ionosphere is at least always there to some extent. It is more constant than the weather and absorbs less energy from the wave than the Earth. It is the best medium available for aiding the long-range propagation of radio waves. If that's the case, we'd better learn something about this ionosphere. We've been using the word. What is it? The sun gives off powerful ultraviolet rays. These rays penetrate the envelope of gaseous matter surrounding our Earth, called the atmosphere. The rays cause electrically charged particles, or electrons, to be separated from the atoms of this matter. The breaking up of a neutral atom into electrically charged particles is called ionization. Each atom, upon losing an electron, assumes a positive charge. When the sun's rays are removed, as during the night, the oppositely charged particles attracted to each other tend to recombine. Even when the sun's rays are in the process of ionizing the atmosphere, the electrons strike the positive ions and regroup into neutral atoms. A balance between ionization and recombination is eventually reached. The balance is tipped in favor of the ionization activity of the sun in the upper atmosphere, where the rays are vigorous and the atmosphere atoms are more loosely packed, making recombination less apt to occur. Here, too, the effect of the rays lingers during the night hours. Thus, the ionization is greater in the upper regions. The stirring up of all this activity naturally takes energy out of the ultraviolet rays. Therefore, less of their initial energy is able to penetrate to the bottom layers. Less ionization, then, occurs in the lower levels. Here, too, since the atmosphere is denser, recombination occurs more readily, and the ionization does not remain long after the sun's rays are removed. This ionized region exists roughly between 35 and 250 miles above the Earth's surface. It is called the ionosphere. The ion density in the atmosphere does not increase uniformly with height. There is a certain separation into discernible layers. This occurs because the radiations from the sun are of different wavelengths. Each wavelength tends to run out of energy at a different level of atmosphere. From the lower layer, the bands of the ionosphere have been given letter designations for easy reference. They are the D layer, the E layer, and the F1 and F2 layers. This is a simplified picture of the ionosphere. Now, how does it affect the travel of radio waves? The process is the same as that which bends the light rays emerging obliquely from water to air, making a stick placed in the water look bent. This is the phenomenon of refraction. The same thing happens when a radio wave travels at an angle between two mediums of different characteristics. When the wave front enters the ionosphere obliquely, the presence of free electrons increases its speed. The upper portion of the wave front encounters the speeding up property first and thus gains a little on the lower portion. This pivots the wave front and changes its direction. The higher the wave goes through the strata of the ionosphere, the more it is bent until it is returned to Earth at the same angle at which it left. The upper portion of the wave front, always being the first to enter the higher ion density and the last to leave, gets more of the speed-up effect throughout its travel. Since the ionosphere grows denser somewhat more gradually than this, the path of the radio wave is better represented as a curve, and the turning effect will be continuous. We now have a stratified ionosphere which refracts radio waves and returns them to Earth, in the meantime absorbing some of the wave's energy, the absorption being greater in the lower ionosphere, where the atmosphere is more closely packed. Another factor now enters, the frequency of the radio wave. White light, or sunlight, as you know, is made up of all colors, each having a different wavelength or frequency. When white light is passed through a prism, its component wavelengths are refracted to different degrees, thus spreading out the light and separating it into the visible violet, blue, green, yellow, orange, and red colors. In the same way, a certain electron density in the ionosphere will refract a low-frequency radio wave more than it will a high-frequency wave. Therefore, a higher-frequency wave, in order to be returned to Earth, must continue upward until it finds a layer of still higher electron density so that it will be given more pushes around toward the Earth. If it is of too high a frequency, it never gets turned around and goes kiting off through the ionosphere into space. Frequency also determines the amount of absorption to which the wave will be subjected. Consider two waves of widely separated frequency. It can be seen that the wave of lower frequency spends more time in the lower ionosphere, where absorption is greater due to higher atmospheric density, which results in a greater number of collisions of the electrons and atmosphere atoms. It is obvious from this discussion that if we are going to use the ionosphere to help us send radio waves over long distances, we are limited in our selection of frequencies. Generally, the longer waves, below 3 megacycles, lose too much energy by absorption. Very high frequencies, above 30 megacycles, on the other hand, are so little pivoted by the turning effect of the ionosphere but they pass through and go off into space. We are left, therefore, with only the high-frequency band. In this range, we can choose a frequency that will not be unduly weakened and yet will be refracted back to Earth. Two other factors affect the propagation of radio waves. These are skip distance and angle of fire of the antenna. We have seen that each radio wave receives a certain amount of bending in the ionosphere, dependent upon its frequency and angle of radiation. Let us take some frequency, F1, and hold it constant for this sequence. Starting with the beam at a vertical angle, tilt the beam until reflection is first obtained from the ionosphere. Let us label this angle as A. Now we have seen that for all angles greater than A, the wave of frequency F1 is lost by penetration, and at angle A, we have the first reflection. The point at which this wave returns to the Earth determines the skip distance for the frequency F1. No signals will be received at less than this distance for frequency F1. For all angles less than A, reflection takes place because less turning is required, and the distance between the transmitter and receiver increases as A decreases. Now, going back again to angle A, since this is the critical angle for frequency F1, then at this angle, all frequencies less than F1 will receive more bending, and the distance between the transmitter and receiver will decrease. Likewise, all frequencies higher than F1 will not be bent enough, and hence will be lost. Although we have talked of rays and beams and shown only segments of waves, we do not mean that all antennas radiate highly directive beams. Quite the opposite is usually the case, and we in our discussion have only indicated the effective usable portion of the wave. Waves are actually radiated from omnidirectional antennas in all directions. The radiations at very low angles are absorbed in the Earth, or lower ionosphere. The upper section, or high-angle radiation, leaves the ionosphere and is lost. This leaves only a small portion of the total radiated wave effective for long-range communication. Now, in review, what do we have? A stratified ionosphere. Electron density of the layers increasing with height. It refracts waves in the high-frequency band. The higher the frequency, the farther the wave goes up before coming down. If the frequency is too high, we lose the wave. The higher the frequency, the less the absorption. The higher the frequency, the longer the jump. When we want to hit a receiving station a long distance away, we send out the highest frequency wave whose effective portion enters the ionosphere at the proper angle to be refracted back to the receiver and yet stay within the ionosphere. There is an area known as the skip distance, where no signal of this frequency will be heard. For longer distances, two-hop transmissions might be used. The calculations for best circuit operation would not be too difficult if these were all we had to worry about. That is, if the ionosphere was stable and its layers rigidly fixed in altitude and density. Unhappily, this is not the case. Since the ionosphere exists because of the ultraviolet radiations from the sun, variations in these rays change the nature of the ionosphere. As night approaches and the sun's rays become weak and disappear, recombination of the electrons with oppositely charged particles takes place, at a much greater rate than does ionization. The D layer disappears, and oftentimes the E layer, and the F layers combine. Thus, the ionosphere varies from day to night. Because of this decrease in ionization at night, the usable frequencies for a given distance will be lower than for daytime. Parts of the Earth are farther from the sun than others. They get the rays at different angles. In polar regions, for instance, with their unusual daylight cycles, the ionosphere is thin, sensitive, and erratic, making radio propagation difficult. Thus, there is a geographical variation of the ionosphere. The Earth's North Pole tips toward the sun in the summer and away from the sun in the winter. This introduces seasonal variations in the ionosphere. Even the sun has changes of mood. Sunspot activity increases in cycles, giving out changing amounts of ultraviolet rays. These cycles seem to vary over 11-year periods, as this graph of sunspot activity shows. Thus, the ionosphere must follow suit and change in an 11-year pattern. This is a slowly changing condition. What about sudden changes? The sun's face is not quiet. Sudden, gigantic eruptions send out abnormal flashes of ultraviolet radiation. These flashes of radiation strike the exposed side of the Earth and cause sudden ionospheric disturbances, disrupting the ionosphere from a few minutes to several hours. These SIDs have a tendency to repeat at 27-day intervals, which is the time it takes the sun to rotate. Besides the rays, these eruptions on the sun send unusual amounts of particles toward the Earth. Arriving later than the rays, the particles enter the Earth's magnetic field, cluster about the polar regions, and disturb the Earth's magnetic field and the ionosphere, causing ionosphere storms lasting for hours or even days. The advent of the abnormal amount of particles from the sun expands the aurora from their usual polar locations to include even the temperate regions. Ionospheric storms usually accompany these heightened auroras. The ionosphere itself has some tricks to play. Unexplained clouds of dense ionization drift through the lower layers. This is called a sporadic E condition. Sometimes these clouds are stable enough to aid in transmission, making operation possible on frequencies much higher than are ordinarily used. Major thunderstorm areas, which are located in the tropical regions, continuously send out electrical disturbances through the ionosphere. These electrical disturbances are transmitted in the same manner as radio waves and are heard in a radio receiver as a loud crashing sound when the receiver is in the vicinity of the storm. But generally, it appears only as a background hiss when the receiver is a long distance from the general storm area. The signal arriving from the transmitting station must be made to overcome the noise to be useful by either increasing the transmitter power, using a more directive receiving or transmitting antenna, or changing to a frequency which is less absorbed by the ionosphere. That'll give you some idea of the problems involved in long-range radio communication by way of the ionosphere and how these problems can be overcome. First of all, we must add to our knowledge by continuous research and study of propagation phenomena. Army personnel in the field and at Fort Monmouth are constantly at work on these special problems. The Central Radio Propagation Laboratory at the National Bureau of Standards conducts basic research and long-term studies in the field. And in order to use our knowledge, we must collect data on current ionospheric conditions for the same reason that the weatherman needs regular observations of air temperature, winds, and the like. ionosphere measuring stations throughout the world constantly check the height and density of the ion layers. Here in Okinawa, an automatic measuring device developed by the Army Signal Corps sends radio pulses of varying frequencies into the ionosphere and automatically records the altitudes from which the different frequencies are reflected by tracing a graph of the layer's heights versus frequency on a cathode ray tube face. Here is basically what the ionosphere recorder measures. The height of reflection, shown in this direction, and the frequency in this direction. Waves of low frequency are returned at this altitude, and the higher frequencies from the upper ionosphere layers at these heights. This is a typical trace. Now, here are actual traces photographed at a recording station. These were photographed in the afternoon. Notice the frequency range and the comparative steadiness of these traces. As the daylight fails, note how the ionosphere becomes less ionized, as indicated by the range of reflected frequencies becoming less and less until a minimum is reached just before dawn. Now, here are a few ionosphere records made during a disturbed period. This is a vivid picture of the erratic behavior of the ionosphere during a storm. Note the turbulence of the layers, how they vary rapidly in height and reflected frequency, or even disappear entirely. From normal day records and other measurements, tables are produced which show the maximum usable frequency and optimum working frequency for known distances at any place in the world for any hour or season. The type of antenna can be determined, as well as the amount of power needed to maintain sufficient energy in the wave for good reception. Different signal intensities are necessary for CW, voice, or teletype service. By observing trends, predictions are published, giving expected noise levels, which may have to be overcome. Use of this data makes it possible for communications people to maintain long-range radio contact by way of the ionosphere most of the time. The Signal Corps Radio Propagation Section in Washington, D.C., together with its Baltimore Field Unit, stands ready to supplement these tables with advice and recommendations to field radio officers. Consulting services are available for the asking on all phases of communications problems. Radio waves are beamed skyward from Army antennas carrying their vital messages to the distant points of the globe. Whether or not the message gets through may depend on how well you can handle the information published in propagation pamphlets and how well you understand those unseen and not always cooperative layers beyond the Earth that make up the ionosphere.